Hello there, and welcome to lesson number 1 from my video series on descriptive geometry. This first video is going to be a little bit shorter than normal. I'm going to introduce the book that we'll be working from, and then we'll talk for a minute about what descriptive geometry is and why we would continue to require students to study the material. After all of that, I'm going to introduce the idea of the glass box and take you on a quick tour of what our screen setup is going to look like and how that's going to help you learn. So the first thing for us to do is to show you the book that our problems are going to be coming from. This is the 9th edition of Descriptive Geometry by E.G. Pair. This is the same textbook that I was working from when I took the class, and because descriptive geometry has a narrow focus, there's a pretty good chance that your class will be using the same book too. I would encourage you to read through what you can after watching the videos, because the text can be very confusing if you haven't had someone to explain what's going on as you go along. However, if you're not using this particular book for your class, or you have something against reading, no worries. The information is the same wherever you go, so there's no need to stress out. Alright, now let's talk about some general understanding first. Descriptive geometry is a fancy way of saying three-dimensional modeling techniques in two-dimensional space. Before we had any sort of fancy CAD programs that let us model things in 3D in real time, there were problems that had to be solved by engineers who worked in the mining industry, scientists who helped design instruments of war for Napoleon, and men who mapped the topography of the Earth. All of this was accomplished with pencil and paper, using the techniques that we're going to learn about over the coming weeks. I want to show you a picture of the Empire Mine out of Grass Valley, California. This is a picture of the mine shaft that you can head down into when you're there. It's a descent of about 100 to 150 feet into the shaft network. But I want to show you a different picture that's more interesting to me, and it's of something that was called the map room. Now, when the Empire Mine opened up in 1850, the model that you're looking at was only accessible by 3 people out of the hundreds of guys who were working for the mine. The map room was so critical to the operation that it was guarded 24 hours a day, 7 days a week, perpetually on lockdown. It doesn't look terribly impressive, does it? It's certainly not enough to warrant that kind of secrecy or security. But what you're looking at right here is a 170-year-old 3D model of the Empire Mine network of shafts, accurate to within 1 foot. Remember that mine shaft that I was showing you just a little bit ago? If you were to stand at the bottom of that shaft, you would have only moved about 1 inch of distance into the model, which gives you an idea of how big the Empire Mine really is. Today, most of these shafts are filled in with water, but that's not really what I want you to pay attention to at the moment. I'd rather you look at the geometric shapes that you can recognize. These guys represent the excavation shafts. Notice how they all have different slopes. This one has a shallower slope, this one has a shallow slope, this one has a pretty steep slope here. And notice how there's access tunnels that are weaving in and out between all of the excavation tunnels. Well, the excavation shafts, there's a problem when you're digging around excavation shafts. You can't dig too close to the shafts themselves because you might weaken the structural integrity and you might cause a cave-in. And typically when you're working at a mine, cave-ins are not an ideal situation to have. The map room was an accurate plan of the mine that was used for excavation planning. Where were they going to dig? What direction would they dig? How far in that direction would they dig? And all of this was generated using descriptive geometry techniques. Alright, enough with the history lesson. Let's talk about the screen layout for a minute. In all of our videos, we're going to do all the actual drawing in AutoCAD, which is always going to be on the left-hand side of the screen. On the right-hand side of the screen, we're going to have SOLIDWORKS running to help with our 3D visualizations of the objects we're working with. In descriptive geometry, it's more important to learn the procedure rather than lean on your brain's intuitive ability to manipulate objects mentally. So throughout these videos, we will typically be drawing simpler shapes so that you can be more focused on the logic of the procedure rather than the shape of the object we're trying to define. But I think it's going to be helpful if I can take some of that visualization workload off of your shoulders while you're learning, so we will always have some sort of 3D rendering happening over here on the right side of the screen. So our next topic is going to be the glass box, which you can see here we have a model in SOLIDWORKS to look at. The object that we're actually going to be drawing is this blue box that's sitting in the middle, and it's encapsulated around by this container right here. That's the glass box that your professor is always talking about. Although the word box is kind of a misnomer to me, because it suggests to me sort of like a regular shoebox type shape, and I don't have a regular shoebox type thing drawn here. I've got like some weird cutouts going on. I've got a two cutout going here, and I've got one going here. It doesn't quite look regular. When we say glass box, what we really mean is a container that fully contains the object that we're trying to draw. It doesn't matter what shape it has, but it can't have any curves. It's made solely of flat surfaces. Each planar surface represents a normal view of the object, and it has a distinct name. For instance, the name of this plane that I've highlighted right here is number 2. When I say normal view, what I mean is that when we look through the surface to the object, the assumption is that the direction of our vision is at a right angle to the plane that we're looking through. Let's go ahead and open up a red cylinder right here that represents the view, our eye, looking through the object to the object that we're trying to draw. You can see if I give us a horizontal view, a top view of the object, that our eye line is perpendicular to this line right here, which represents plane number 2, because we're looking straight down the top. We would see plane number 2 as just a single line, and you can see that those two things are at right angles to each other. This assumption is always going to be true in any problem we do. We're always going to assume that we look through a view at a right angle to the plane that we're looking through. It wouldn't be very productive if we assumed otherwise, so we're just going to assume that that's always true. So, the next thing I want you to take a look at is I want you to take a look at these letters which have been scribed onto the box. Notice how they're different. Up top I've got an H here, down here I've got a 2. And what those represent are identifiers for the specific planes. The H up here represents the top plane of glass that covers the object that we're trying to draw. It's represented by an H because we call that view the horizontal view. You'll sometimes also hear it referred to as a top view, but in descriptive geometry, it's typically, the nomenclature is typically used as a horizontal view. That's what we're going to stick with. There are other letters that you might see. You might see one of these as a P, that stands for profile. And over here you'll see there's an F down here, that stands for frontal. Now the next thing I want to do is I want to open the box up for you. So let's go ahead and take the fold and we'll suppress that guy. And we'll take a horizontal view of our object. Again, here's the object that we're trying to draw. And now we can see all of these squares, which represent the planes of the box that encapsulate the thing that we're trying to draw. Now, how exactly do you tell the difference between which plane is which? Well, thankfully our letters came along for the ride. So you can see that between this really, really thick line right here is an H on this side, indicating that everything over here is on the horizontal plane, and a 2 on the underside of that really thick line, indicating that everything that you see down here is on the plane marked as number 2. You can see that that's true everywhere. Here's an H, everything below this line here belongs on the horizontal plane, everything above belongs on plane number 1. Here's horizontal and profile, and horizontal and frontal. I want you to pay attention to the direction of two lines in particular. I want you to pay attention to the line H and 1 right here. And I want you to pay attention sort of to the orientation of this really thick line H and 2. Because that's going to be important for us a little bit later. So let's fold up the box, hide this guy, and return back to our standard isometric view. It's time to move over to the AutoCAD side of things and take a look at the actual descriptive problem that I've come up with, descriptive solution that I've come up for this same box. This drawing, these are what all descriptive geometry problems are going to look like, but they describe the same object. The only difference between this drawing here and this drawing over here is that I haven't drawn the entirety of the glass box to show you literally, as I've drawn it over here. So let's take a tour of the different kind of lines in the descriptive solution over here on the left-hand side of the screen, and what they mean. First thing I want to show you is I want to show you these white lines right here. Anytime you see a white line in any of your drawings, those are called object lines. And object lines define sort of the rigid profile, the actual edges of the object themselves. For instance, in our SolidWorks model, this line right here would be an object line. So would this line. So would this line. This line over here would not be an object line because it's not actually part of the object we're trying to define. The next thing I'd like for you to take a look at is these green lines right here, 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 and here. These are called folding lines. Folding lines represent where two planes are intersected over an object. You can almost see here in the 3D model that the line, it's where the box is folded over. And those are always going to be represented by green lines. Notice how they also carry over some letters. Here's the H and the 1, H and 1 through that line. Here's the H and 2 for this line right here. Here's the H and the F for that line right there. Folding lines are part of the glass box and are not part of the object that you're actually drawing. But they're useful for orientation, and they help us track which two views are being talked about. The yellow lines, lines like this one, maybe this one over here, are called projection lines. And what they represent is connective tissue between the two views, say H and 1 in this case, where they talk about, they connect point to point, point to point. They help us, they tell us which information is being shared between two views. I want you to notice how there's a little A in each view. There's one right there, one here, here, and here. In descriptive geometry, what those little letters are telling you is that this A is the same point as that point right there, which is the same point as that point right there, which is the same point as that point right there. In our three-dimensional model, that point A is represented by that little yellow ball sitting right there on the blue box that we're trying to draw. Now, the last piece of geometry that I'd like to discuss is this purple line right here and right here. Those are called hidden lines. And hidden lines are object lines, but they're hidden behind a portion of the solid object, so we can't really see them. So it's not fair to draw them the same as object lines, because object lines are things that we can see. Hidden lines are also object lines, but they're things that we can't see, and they're going to show up a little bit later. So we draw them as these purple dashed lines. So let's take a look at our 3D model from views number 1 and number 2 and see if it matches up with the descriptive solution that we have over here on the left side of the screen. I'm going to go ahead and open up the View Manager, and let's take a look at plane number 2 first. Let's turn that glass box off so that we're just looking at the object itself, and let's turn hidden lines on like that. And I'll close that guy down. Let's get in a little bit closer. So, view number 2. Notice how that point A right there is exactly where we predicted it would be. And notice how there's a hidden line right there, which you can see here. If we were to turn this guy back on so that we could see it in color, and we turn this guy over, look, there's that edge right there. That's that hidden line. We go back to plane 2, and you can see it through the material. You're looking through the material to that edge. Now, let's take a look at view number 1 and turn on hidden lines. Let's recenter that guy so we can get a really good look at it. You'll notice that point number A right here is the same, exactly where SolidWorks predicted it would be. And you can see a hidden line right here. Again, right where, if we were to turn this guy, there's that hidden line right through the material. So we'll take a look one more time. Plane number 1. We'll return back to an isometric view. And we'll turn this guy back into a solid shape, nice and colored so that we can see it. So Ultimately, what this is saying is that the prediction offered by our descriptive solution over here on the left side of the screen agreed with our super fancy software that predicted the exact same thing. So that's going to go ahead and finish everything that we're going to cover today in lesson number 1. And I'm going to see you next time.